approach for classification is we have samples for two classes, and we fit probability distribution for each class sample independent of the other class samples. So we are not directly coming up with a decision boundary. It's a generative approach, not a discriminative approach, right? And for the test samples, what do we do is once we get a test sample having the features X or whatever dimension, it could be one dimensional, two dimensional, whatever, we look at which class probability distribution is most likely to generate that sample. And the class which has the highest probability of generating that sample, we assign the same class to that sample, the test sample. And to get that, we basically work with the joint probability. So we have P of X given X, the joint probability of X and Y. X is the feature values and Y is the class, right? Is nothing but P of Y into P of X given Y. The probability, the prior of the class and the likelihood of generating the sample X from a class distribution Y, right? And we say that this is nothing but coming from the Bayes rule, right? So this is basically coming from the Bayes rule. In a sense, we know that P of Y given X is nothing but P of Y into P of X given Y over P of X. And P of Y is the prior, which is sometimes also denoted as pi. And P of X given Y is the likelihood. And the P of X, the denominator, is the marginal. And the final thing, the P of Y given X, the P of Y is the class given the samples X is the posterior. So this is the actual equation which you need. But we know that for any class, so for example, if you're speaking about the probability of Y being class 1, so what's the probability of Y being the first class given the sample, the test sample X? We know its probability of Y equals to 1, the prior of first class, times the likelihood of generating X from the first class over the denominator, which is the probability of X, which is the marginal, right? And this is basically a normalization term. And if you see P of Y equals to 2 given X, it's the same thing, the prior of class 2, the likelihood of generating X given the class 2 distribution over the P of X. And because all those will have the denominator being P of X, you don't need that to make a classification decision, because the values will only depend on your solution will only depend on the numerator. So you look at this thing, P of the prior times the likelihood. And we also spoke about the idea that if you believe for some reason that you should not take into account prior, in a sense that you have a belief that in your test, the samples of different classes can come with equal probability. So what you will do is you will just ignore the prior. You'll not consider it. And again, this is just a designer's choice, right? You make a decision whether you want to put this into equation or no. Do you want to consider priors or no? Okay. Good. So then we move to the next thing is, so what about the parameters? How we are going to learn the parameters of the modeling, right? So what we speak about this is that let's assume this case. In this case, of course, we have only three classes and one feature. And what we can do is for estimating the priors, we can look at the training samples and just find the ratio of every class samples as compared to the total samples, right? So assuming that in this case, pi1, the prior for the first class was 0.1, which is 10%. Prior for class 2 is 50% or 0.5 probability, or prior for 3 is 40%, which is 0.4. So assuming that the total number of samples in that that training was 200. So basically what it's telling is we had 20 samples of class 1, we had 100 samples of class 2, and the remaining 80 samples of class 3. And that's why we are getting these priors. Okay. Now, what about estimating? So prior is just a count, right, from our training samples. Count of the samples belong to a given class. Now, what about the likelihood? How do you come up with this likelihood thing? Now, to come up with the likelihood, the P of X given Y, we have to fit a distribution, right? And the question would be now, which distribution should we fit? And we can fit different distribution depending on the problem. But in a general sense, if we don't have a very specific reason of fitting a specific distribution, we can use the Gaussian distribution, right? Or the normal, which is also called as the normal distribution. I hope this is clear, right? So again, as I said before, so if we don't have any specific reason, we are going to assume this to be, I'm sorry, a Gaussian distribution. And we'll see in a later class that That's not the only choice. We can have different choices. For example, you can have Bernoulli distribution, gamma distribution, different distribution depending on your the nature of your features, right? But generally speaking, if it's a very general idea, you can always use Gaussian distribution. But before going into the details of that, let's look at it and make some try to make some sense out of this. What is saying? So if you see here, we have these three class distribution, and you can see this bell curve. This is the normal distribution. So assuming we are already using normal distribution, so let's see this. Assuming, and this is the feature, right? So assuming the test sample has a feature value, let's say somewhere here. So what do you think will be the class for that sample? Again, keep in mind this is one dimensional, so it's only one feature, right? So if this class has only one feature, yeah, and this test sample is of having a value of something here. So if you see the distribution, it looks very obvious that the class would be the first class, right? Because that will have the overall highest likelihood. Good. What about if it is somewhere here? This also looks obvious that it's going to be a class 3, right? But think about this. What if the feature value for a test sample was here? So it cuts here, right? So the probability, the likelihood for class 3 would be a very small value, and the likelihood for class 1 and class 2. So P of X given Y for class 1 and class 2 is going to be exactly same. Now, if that is the case, which class are you going to assign this test sample 3, S3, to? Because both of them have same likelihood, which is P of X given Y, but you know that the prior is different. So the prior for the first class, and if you see the P of X given Y, both of them have same P of X given Y here. But pi 1 is smaller than pi 2 in this case. So what do? You will assign the sample 3 to class 2. I hope this is clear, right? So again, if you have a question, please let me know. So basically, if this is the test sample, you'll assign it to class 2. Good. Okay, so let's now move forward. So we spoke about the idea that we have to fit a distribution to the samples of a class, and if there is no specific reason to select a specific distribution, we can use a normal distribution. Okay, so this the Gaussian distribution, of course, is a bell-shaped thing. Okay, so what do we do is Okay, so let's now try to visit this thing. So as we said, this is a Gaussian distribution in one dimension, right? So assuming you have features, only one single feature, right? So this is what happens. A Gaussian distribution basically has two parameters. You have the mean, which is the mu, right? And you have the standard deviation or the variance, right? So normally we say the distribution is, a normal with mu and variance. So this is mu equals to mean, and sigma square is nothing but the variance. So a Gaussian distribution has these two parameters. And you can see the likelihood is highest at the mean. So mean is the center, right, of the bell curve. And as you move away from your mean, the probability, the likelihood goes keeps going down and down and down as you go, right? So this is the idea here. So it says that actually it's almost 95% of the probability mass, the area, is covered within mu plus minus 2 standard deviation, right? So there are some very general properties of the Gaussian distribution or the normal distribution. You can always check it out. But keep in mind that if we decided that our samples would be fit using Gaussian distribution, we basically need only the two parameters for this distribution, the mean and the variance, right? Basically, you can calculate the mean as the sample mean, and the variance you can basically calculate the standard deviation and the variance. These are basic normal statistics, right? You can use the training samples to come up with these values. Okay, good. But then if you have these probabilities, right? I'm sorry, if you fit your samples to a Gaussian distribution and you estimated the value of mean and variance from your training samples. Now the question is, what's the probability distribution function for the likelihood? So we know that to make a decision, we say we want P of y given x, which is nothing but P of y times P of x given y. And to know this, we are saying that we are fitting a Gaussian distribution, right? So what is the probability density function for Gaussian distribution in one single dimension? So in a sense that you're speaking about only a single feature. So we have the PDF is given by the function. And if you see, the probability will only depend on the value of x, right? How far you are from the mean. Of course, if you are in the mean, you have the highest value. As you go away from the mean, your probability likelihood keeps going down and down. And the PDF is nothing but this equation, right? 1 over square root of 2 pi, right, times sigma e to power of, what do we have? We have, I'm sorry, x minus mu square over sigma square. This is the PDF for one-dimensional Gaussian, right? So you see that for a given sample, it only depends on x. So again, this might look a bit messy as an equation, but let's try to understand a few things here, right? So of course, one of the things is it's an exponential distribution, right? So Gaussian is as an example of an exponential distribution. Keep in mind, we said that the likelihood will be highest at the mean, right? So basically, if x is mu, x is same as the mean. If it's here, it has the highest probability, and which will be nothing but 1 over square root of 2 pi times sigma e to power 0, because this whole becomes 0, everything e to power 0, which is 1. So this is the value you get, the likelihood value, 1 over square root of 2 pi sigma. So this is the value here, right? Which is 1 over square root of 2 pi times sigma. And as again, trying to just make some intuitive observations here, you have this negative one, right? Why it's negative is because keep in mind that it's a probability, and as you go further, right? So x minus mu square, this increases, and your probability keeps going down. It keeps going down, right? So this is also another thing to keep in mind. And this term, and of course, there can be one distribution as an example. So let me just take something here. Okay. Yeah. So let's take a bell curve here. Okay. And opposed to it, we have another one which is more spread off. So how far your x is from the mu is one thing, but you have to keep that in perspective of based on how much the spread is. And that's why you have this thing here, right? So with respect to how spread the distribution is, how far your probability likelihood is going down depends also on your spread of the curve. And what about this last thing here? This part, this is basically the normalization thing, because we know that if you look at the whole probability of all the possibility, the whole area under curve, it should be 1, right? The probability of the whole thing is just 1, right? The integration of over all the area. So that part is basically the normalization thing for the probability. So these are some intuitions again. If you want to know how to derive this, basically it's a statistical problem, and there's a lot of material available on books and online just to see how to come up with the duration for the PDF of Gaussian distribution. So, but for the timing, just keep that into perspective. So it's an exponential distribution. You have this normalization term here because you want the area of under the curve to be probability is 1, and it's an exponential with negative because as much you are. Yes, please.
So as the Gaussian become more sharp, so we are more certain.
Yeah, that's also one phenomenon. So what you're thinking about is the mass is 1. So if you are spread out, so this peak will be lower. But again, the same area, you're going to stretch it up if you want to make it sharper, right? So basically what we are saying is if you have low variance, low standard deviation, you'll have a sharper curve. And this point the likelihood will be higher as compared to this point, because at the end, this whole area is stretched in a very narrow bell curve. I think this was your question.
The screen disappeared.
Okay, is this now available now?
Not
Can you see
yet.
it?
Yes, clear.
Yes, now. Yeah.
Okay, good. Yeah.
Yeah, thanks, Doctor.
Okay, very good. Yeah, so it's basically a PDF. It's a likelihood, and the sharper you have the distribution, you have these taller, in a sense, taller bell curve. So the likelihood is much higher in that sense, of course. But we'll see later on, we also have to be careful about overfitting, what we also spoke in terms of SVM, right? So the spread, if higher spread is there, so it's more generally speaking, less overfitting. But again, that's a different topic. We'll come to it later on. So this is our basic idea of the normal distribution, right? So what we are saying is, if you once we assume that our distribution will be normal from the training samples, we want to get the prior, which is based on the count. And for each class, we just look at the samples, find its mean, and the standard deviation. And basically, that's all what we need to know. Now, once we get a test sample, we just apply that PDF. I'm sorry, why every time it's going down? And I know it will be again off, so you'll see it just a minute. So it's somehow crashing. Okay. Good. So yeah, is there any question, or we move forward?
No question.
Okay, very good. So now let's. So is this clear? So what you are going to do, if you are going to do this type of modeling, the generative modeling with one dimension, what you need to do is you just look at the samples of a class, and based on the samples of the class, you have to, I'm sorry, basically just find the prior. And for each Gaussian, for each class, you just estimate the mean and the variance, and that's it. Once you have a test sample, you use this equation. Basically, you just find the pi of a class I times p of x given y, or is that class I. And pi of I is the prior, which is based on the counting. And how we find this is basically using this equation, where you have the test samples x. Based on that, you get the likelihood. You multiply these two. You do this for all the classes, right? So again, let's go back to the previous example here. So if you have three classes, what will we do? If we get a test sample x, we'll see pi 1 times p of x given y equals to 1. We'll see pi 2 p of x given y equals to 2, and the prior 3 times the likelihood of generating x from the third distribution. And whichever of these three is the highest, we assign that class. And this is basically the PDF, what we spoke about just now. Okay, good. So if there's no more questions, let me go forward. So let's take this example in the IRIS dataset, right? So IRIS dataset is also a good case study for machine learning. It's a very old dataset, but still it's good to use it as a learning experience. So here what we have is, in IRIS, you have these iris are the flowers, and you have three different species, right? So you have Iris setosa, Iris virginica, and this versicolor. And basically what happens is you have only 4 different features. You have the petal length, petal width, the sepal length, and the sepal width. So these are the 4 features, and there are 3 classes. These are the 3 different classes, and iris flower. These are the 3 different species in that sense. And basically, you have only 150 samples given and divided into training the test set. So let's see what we have here. In this, if you fit generative modeling, it's let's say there's a species, this called the species 0, species 1, and the species 2. In the training, out of 150, 105 samples were allocated for training. You have 33 samples of class species 0, or class 1, whatever you call it, 34 samples for the second class, and the 38 samples for the third class. Okay. So basically, what will be the pi 0? The prior for species 0 is nothing but 33 over 105. For the species 1, the prior is this, and the species 3 is this is the prior. Okay. And now let's assume we are going to do the classification using only a single feature, which is petal length. Okay. So basically, we are going to use the petal length as a feature to fit a normal distribution. Okay. So this is what we get basically. Okay. So this is the petal length, and this is the likelihood based on the training samples. So you can see for the species 0, the mean is actually 0.31. This is the mean of the petal length. For the no, I'm sorry, this was the prior, right? So 0.031, 0.32, and 3.7. These were the priors for the 3 species, and the probability distribution, if it's a Gaussian, we hit a Gaussian. For the species 0, the mean is 4.96. So what we are speaking about is the mean is somewhere here, right? 0.96. And similarly, the mean for the second class, the species 1, is very close to 6. It's 5.90. And similarly, 6.49 is the mean for the third class.
I got a question here.
Yes, please.
So you said we have a training, we have 105 samples.
Right.
For the first one, we have around 33 samples. We have to have.
Yeah, we have 33 samples.
Yeah, so we're going to calculate the mean of these 33 samples.
Yes, you're very right. So we are going to, as we said, we are going to model each class independent of the another. So we are just finding the mean of 33 samples to find. So what is this? Yeah, it's a very good observation. So what is this mean? This mean is only the mean of the 33 samples of class 1. So you have the petal length for class 1. Let's assume some of them are 4, 4.9, 5.6, 5.8, only for one class, only for this class, the species 0. And its mean is this one, 4.96. Similarly, what's the mean for species 1 is basically all the samples only for class 1, species 1. We just find the mean of that. And it's the same thing we do the mean for the species 2. Yeah, so that's right. You're right. Similarly, we find the standard. Yeah. Okay. And then the distribution. So you can see that the standard distribution, standard deviation or the variance for the class 1 is 0.37, which is narrower. You can see that the bell curve is narrow and high. And the second class is this one. So it is a bit wider than the first one, and the third one is the most wider. So this green one. And you can see that the peak is lower as compared to the second one, and the first one has the highest peak. And of course, we understand that each one of them, the area under the curve is 1, the probability mass. Good. So if you have this, then what do? In the test set, you basically get the petal length for a sample, and you just make a classification based on that. So again, I have a question now. Assuming that this point, okay, assuming this point is 5.5, assuming it. So what if I have a test sample whose petal length is 5.5 millimeter? Which class I'm going to assign to it? You see the likelihood for species 2 is very low, which is almost like 0.1. The likelihood for a species 0 and 1 is exactly the same, which is assuming it's 0.5. So which class are you going to assign now? Are you going to assign it to species 0 or species 1?
Species 1.
Right, because it has a prior, which is a bit more than species 0. So, and that's why you're going to assign it to species 1, which is, yeah, species 1. Exactly, that's the idea here. So if you see the test error on the 45 samples, you had 12 out of 45 was mistaken based on this idea, which is the error rate is 26.6 sample, 26.67%. So in a sense, it's not too good, but at the same time, you're only using one feature right now, but it's still much better than a random guess, right? So random guess, you're assuming because it's also the distribution is almost same. So you're guessing you can get a random guess would be almost like 63%, right? So you will, if you do a random just based on the prior, you will say everything is class 2, for example. So you can get something close to 63%. In general, it will be the error would be close to 2/3. So yeah, of course, it's much better than that, but still not very. The error rate is still high, but we use just one feature here. So any question on this before we move to the generative modeling? The generative modeling using two features instead of only one.
Doctor, the error here was based on the test sample, yeah?
Yeah, on the test sample. That's why it's saying it made 12 mistakes out of 45 test samples. So 12 out of 45 was mistaken to wrong class. So the error is 26.67. And basically, you can see also visually why you will have those type of errors, because you have also good overlap between the distributions, right? So samples which are around here or samples which are around here, you see this is going to confuse between the two classes a lot. So it makes sense that you have this type of error. Yes. So is there any question before we move to using the same generative approach, but now instead of using only one feature, we are going to use two features. So what changes? We'll discuss that. So generative modeling with two dimension in two features. Any question before we move forward?
There is one question.
Yeah, please.
We considered here distribution as a normal. What if
Yeah.
the actual distribution would be different in this case?
Yeah, that's the thing. So we will speak about this at the end of this discussion, not today, but once we complete this Gaussian distribution, is if you know for a certain reason, you study your data and you see, for example, let's just give an example because you already asked this question. Let's assume all your features are only positive value. It's real numbers, but positive only. Right? So
Yeah.
Gaussian in general might not be a good distribution because Gaussian can be negative, positive, all real values, right? So maybe
Yeah.
you'll use another distribution, for example, a gamma distribution. You see the thing. What if your value, your features are only Boolean, 0, 1, true, false, whatever, something like that. Again, this is the Gaussian is not the best choice, right? So instead of Gaussian, you might use, for example, Bernoulli distribution. Right?
Okay.
Boolean value.
Yes.
So yeah, the distribution, but we are saying in general, for many of the problems, real world problems, the features are real valued and it could be anything between negative and positive values. So generally speaking, Gaussian would be a good choice to start with. But of course, if you have a reason not to use Gaussian, you will not use Gaussian, you'll use something else. Right?
Yes.
Okay, good. So if there's no more question, I'll move to using two features. Okay, good. So now let's move to Gaussian with two features. So again, as a motivation here, we are speaking about, yeah, we use petal length and we got an error rate of 26.67. What if we use two features? For example, we use petal length and also petal width, not only one of them. So now again, if you're going to fit probability distribution in two dimensions, and again, assuming it's a Gaussian, then you're going to get a two-dimensional Gaussian distribution, which is something like this, right? You get something like this, a bell curve in two dimension. This is something like, yeah. So then the question is, what changes in our problem? Okay. So now what will change is basically you still have the prior. So the prior is already there. In two dimensions, you still have the prior, which is same, exactly the same, how you calculate based on the counts, priors of a class I. But then instead of having mean as a single value, you're going to have a mean vector, right? So assuming if you have two features, for each class, you're going to have a mean vector, which is mu for feature 1 and mu for feature 2. I hope this is clear, right? But now in a Gaussian, right, what happens to the standard deviation? Now, because it's two features, instead of standard deviation or variance, now you have something called covariance. And a covariance is a 2 by 2, assuming we have two features only. So we have a 2 by 2 matrix. Covariance matrix is a square matrix. And if you have two features, you have a matrix of 2 by 2 dimension, right? So in this case, it's a matrix of 2 by 2 dimension. What do you have these values in covariance? In covariance matrix, the diagonal elements are the variances of each feature, right? So you are going to have the variance of the first feature, the variance of the second feature. But what about the non-diagonal items? So here you're going to speak about what is the covariance of feature x1 and x2. And this is same as what is the covariance of feature x2, x1. Basically, covariance of both of them are same, right? So it's a symmetrical matrix with diagonals having the variances of the feature and non-diagonal elements having the covariance of each other, right? So this is the idea here. And this bell curve, what we spoke about, you see here, this will be the peak. So this will have, if you have the feature x1 and x2, which is the mean vector, you find exactly that's the peak, that's the highest likelihood. And as you keep going away, from your mean, your probability, the likelihood keeps decreasing, right? And to show bell curve, of course, visually looks nicer, but to interpret it better, we also can show it as a contour plot. So this is an example from the iris data set here. So you can see this is the same thing. So this is the bell curve. This is the highest point approximately here, right? So you're speaking here, the mean vector 4.96 and 3.43. So the 4.96 is here and 3.43, right? So this is the highest peak. So you can assume some sort of the bell curve, something like this, right? And these contours are saying that all these have the same likelihood. So it's almost like going further and further, right? So this, in the 2D visual plot, you can see here, I'm sorry. Come on, I have to. This is the same thing, the contours. As you go further, your likelihood keeps decreasing. Okay, so this is what we have. So these are the contours. The highest is here. As you go further, and further, your likelihood keeps decreasing. And if you see the covariance matrix, so what is this one? This is nothing but the variance of the first feature, the petal length, and this is the variance of the second feature. And this is the covariance of x1 and x2, and this is same as the covariance of x2 and x1. So it's identical in that sense, right? It's symmetric. Any question on that? Now the idea is, how do we estimate, right? Covariance. How do we find the covariance between two features? So again, I guess just to recap it, this nothing changes, so that's straightforward. The mean, because you have two features, now you have the mean of the feature 1 and mean of the feature 2 per class. So this is a new thing. And then you have this covariance matrix where you have the variance of the first feature, the variance of the second feature for a given class, and now you have to estimate the covariance of x1, x2, which is same as covariance of x2, x1. So what's the equation? Well, how do we find the covariance of two features? Which basically what is, before even going to the details, we are speaking about the dependence. So covariance between two features is explaining or modeling the dependence between feature 1 and feature 2. Okay, so how do we find the covariance? So covariance, we find covariance of x1, x2 is nothing but the expected, the mean of x1, x2 minus the expectation of x1 times expectation of x2. So you find the x1, x2, the expectation of it, and you minus from it the expectation of x1 times expectation of x2. Just to take some examples, right? To make sure we understand what we are speaking about. And basically, again, I'm saying covariance of x1 and x2 is modeling the dependence, because these features might not be independent of each other, right? So for example, think about a person's height and weight. So we know that height and weight are, let's assume we are doing some classification and we are using height and weight of a person as two features. But we also know that height and weight are not totally independent. In general speaking, the height and weight has a positive covariance. A covariance is positive and correlation is positive. So in a sense, the higher, in general, the trend is the higher the height, the higher the weight, in general speaking, right? So what we also call it is a positive correlation. And a positive, the covariance would be positive. Any question on this? So again, if we want to make it clear, let's take some examples, right? So let's take first example of, okay, let's add a page as an example here. So let's take example, again, just to speed up the calculation, I already did offline, so I'll share it with you right now. So assuming that we have two features, x1 and x2, and these are the values for some samples. So I have 3, 7, 2, 4, 4, 4, 5, 9, and 6, 14. Assuming these are the samples. So I have 5 samples and these are the values. So for sample 1, these are the x1, x2. The sample 2, these are the x1, x2. These are the sample x1, x2 for sample 3, sample 4, and sample 5. Okay, these are our samples. So let's write it down. Sample 1, sample 2, sample 3, sample 4, sample 5. Assuming these all samples are for one class. So how are you going to find the covariance and the correlation between x1 and x2? Okay, so just look at it before finding the actual numerical values. Think about it. What do you see the trend? If x1 increases, what happens to x2? It also, generally speaking, it increases, right? So we say that the covariance, we know that the covariance will be a positive value, and it's a positive correlation. Okay, as opposed to if you increase x1 and x2 decreases, then there's a negative covariance and the correlation is negative. So let's try to find out the exact values. So what is the expectation of x1? What is the E of x1, which is the mean of x1? If you do the calculation, 6 plus 5 is 11, plus 4, 15, plus 5, 20, 20 over 5, which is nothing but 4.0. Similarly, what is the expectation, the mean of x2? Again, if you do 14 plus 9, 23, plus 4, 27, plus 4, 31, plus 7, 38 over 5, if you do using calculator, I did it offline actually, just to save time, you get 7.6. And you can verify. If I'm making a mistake, please verify it. So you get 7.6, right? Now, what is the expectation of x1, x2? So for finding that, you just multiply x1, x2. So what do you do? 7 3s are 21, 4 2s are 8, 4 4s are 16, 9 5s are 45, and 14 6s are 60, plus 24 is 84, right? So this is x1, x2. So what is expectation of x1, x2? You basically find the mean of it. So you add all of them, divide by 5. Again, if I'm not wrong, you can correct me if I'm wrong. It gets to 34.8. Okay. So how do you find now the covariance? So the covariance of x1 and x2, which is same as x2, x1. Again, I'm repeating it. Covariance of x1 and x2 is nothing but expectation x1, x2 minus expectation of x1 times expectation of x2. So if you just put this values here, these value here, 34.8 minus 4.0 times 7.6, right? Which is nothing but, again, I did some calculations offline. It gets to 4.4. Again, you can correct me if I'm wrong, right? So this is the covariance you get, 4.4. So this is the thing, one of the things, the covariance value is raw. It's not normalized in a scale, right? So it can be anything, 4.4, 10.8, 100.6, minus 36.8 if you have negative correlation, and minus 100, minus 1000.5, anything is possible. But we know the maximum a covariance can be is the standard deviation of x1. So the maximum absolute value. So absolute value of covariance is nothing but standard deviation of x1 times standard deviation of x2. That's the extreme. You can go positive or negative. Okay. So using this is the concept of correlation. So let's understand correlation. So what is correlation? Correlation of x1, x2 is nothing but covariance of x1, x2 divided by standard deviation of x1 times standard deviation of x2. And again, offline, I did some calculations to find the standard deviation. So what we have is standard deviation of x1 is, let me see what I did, it is 1.414 approximately, right? 1.414. Similarly, standard deviation of x2, you can do this calculation yourself, is nothing but 3.720. 3.72, I'm sorry, 0. So if you just put this in the equation, so covariance was 4.4 and divide by 1.414 times 3.72. What you get is 0.836. So you can see that the correlation is a very strong positive correlation, because we know the correlation, because it's normalized, correlation is in the scale of -1 to 0 to +1. So the highest is +1. So you can see 0.836 is a strong positive correlation. Okay. -9.99 would be a very strong negative correlation. In a sense, if x1 increases, x2 decreases very strongly. And zero correlation means you have zero covariance. In a sense that the features are not, it's all spread. In a sense, in a weak sense, we can say that features are independent of each other. Actually, if you have two features which are independent, their covariance would be zero. So independence means zero covariance or zero correlation. But actually, if you have only zero covariance or relation, it does not guarantee independence. That's another issue. But at least for the time being, we understand that if there is zero correlation, the features, in that sense, in a loose sense, we are speaking about the features being independent. Is
Yeah,
this
doctor.
clear? Anyone has a question?
Doctor, I have a question,
Yeah.
please.
Yeah.
You said that the maximum covariance is the standard deviation of x1 times the standard deviation of x2.
In
This
absolute
is the
sense,
maximum
because
value.
negative, positive, both ways.
Yeah, but how is there any thoughts? How did we come up with this formula?
Yeah,
I
you
mean,
can
with
find
this.
it actually. Again, I'm just trying to avoid this because of time, but you can see it's basically the covariance is based on the expectation,
Okay.
right?
Yes.
So so based on that, you're going to find it statistically. Again, there's a very, if you find it on books, statistical books, you can find it, this derivation, why it is like that, because of the expectation of this, right?
Okay.
So how much you can move away from your expectation value. Okay. So you can find this easily, but this is given at least for the timing. This is the fact. So correlation is covariance over standard deviation of x1 over a times standard deviation of x2. So if you plot it, if you have two features, you will find if it's a positive correlation, you'll assuming that this is two dimensions, you'll find the features something like this, right? So you find some sort of positive, the upward tilt.